Hello, welcome everyone. My name is Ricardo Gudwin. I am a professor at the Faculty of Electrical and Computer Engineering in Brazil, and I'm going to present the work, the Robot Life Specification Problem and its challenge to cognitive architecture. Okay. Let's talk a little bit about the title of this work, because maybe you could find it a little bit strange to talk about the robot life specification. But it is important here to understand exactly what is the scope of this presentation. Okay. We are talking about service robots. We are not talking about the usual kind of robots that you have, for example, in industrial environments, where you have those robots that are making always the same kind of work, performing some mounting or for example, in an automobile factory or a thing like that. In this particular case, we are talking about semi-autonomous or fully autonomous robots that have some mobility and interact with people, usually in retail, hospitality, healthcare, warehouse, or fulfillment settings. So the kind of robot that we are talking about is this kind of robot that you can see in these pictures here. So it could be, for example, a kind of a mechanical arm that is giving some aid for the mounting of a device, for example, or it could be a kind of robot that is helping, for example, in showing an environment for someone, or it could be in the lobby of a hospital, for example, entertaining people or giving some kind of information. So this field of service robotics is a field that is still starting to begin. We don't see too many examples of robots like this in the field. I mean, service robotics are not that common as robots that you can find, for example, in industry, in automobile companies, for example. But in some places, like for example in Japan, service robots are starting to become more and more common, and in the near future we are going to see more and more service robots to be more common in our everyday life. Okay, so this is the kind of robots that we will be talking about in this talk. Okay, well, if you are talking about service robotics, then a second question that comes is, well, how do we design them? How do we project, how do we specify the details of a service robot? Okay, usually these kinds of robots, they have a kind of a fixed repertoire of tasks. For example, they need to have voice communication. For example, they can have speech and listening comprehension, so you can talk to them and ask some questions and they can have some reply. Of course, that these need to be at this current point very simple questions, because we still don't have too many complex abilities for robots of this kind. But anyway, there are some service robots that are able to perform quite good in some cases. Okay. Also, in some situations we can have vision, mobility, some gestures. For example, the robot can try to imitate a human person such that you are talking to this person. Usually, we also have a quite limited scope of missions. For example, a service robot could be designed for a very limited kind of question and answering. For example, where I can find such and such person, or where I can find such department in a company, or how can I discover such and such thing. Service robots can also be used, for example, for making a tour around known areas, for example, in a showroom, for example, in a company where you want to show specific areas in the company, or in specific situations where you want to make some demonstrations. Then you can also use service robots like that. In some situations, you can use service robots for exploring and mapping known and unknown terrains. For example, in mining, you can use, for example, service robots to go into a specific point in the mine that there is some danger of the mine going down, and so you don't want to risk a human person to go in there. Or in handle of catastrophes, for example, during some accident, for example, like in a nuclear disaster, where you want to go to specific parts of the building that has been damaged, and you don't want to risk a person to enter in this place, then you can use a service robot for doing that. So there are many situations in earthquakes or in nuclear disasters that service robots can be used for exploring and mapping the terrains where you don't know exactly what you're going to find in the middle of the way. Okay. Usually service robots are also used for surveillance. For example, you can have a service robot during the night going along a factory or a warehouse, making the surveillance of the place, just like a dog, for example, going around, but in a more organized way. Making auditioning, for example, like in this example that is in the picture, in supermarkets, for example, checking if there is some product that is missing in the shelves. Cleaning, for example, just like these robots that perform some cleaning in houses. So this is the kind of robots that are service robots. Okay, and how we design these robots. Okay, nowadays the design of these robots is limited to the kind of missions or to the kind of tasks that we want these robots to perform. Okay, and they are quite limited in some way, because if you want this robot to perform surveillance, then you give the robot a map, and the robot is going to follow this map and it's going to take pictures, and it is a very limited kind of thing that the robot is going to do. Okay, but this is not going to be like that forever. Okay, and this is when we need to think about what we are calling here the robot life problem. Okay, well, we can see that today's use of service robots or service robotics, they have major limitations. Why? Because they still require the assistance of human beings for a lot of things. For example, for replacing and recharging batteries, for turning on and off the services. They are basically more evolved or more elaborated kinds of toys that you turn on and you turn off and you replace batteries, okay, and put them to work, and that's it, okay. So in fact, what happens is that they have a limited practical use and they are not much more than a toy. In other words, they are not designed for non-stop use. Okay, they are something that we turn on and then we turn off. Okay, but then, and this is what we are trying to address here. What if, and this is what we are calling here the Robot Life Specification Problem. How to conceive a full-time operational robot responsible for its own energy maintenance, with its own duties and responsibilities, able to prioritize and to schedule its own activities around the day, interrupting its planned activities in virtue of new facts, aborting decisions not necessary anymore, improvising in virtue of unpredictable events, interacting with human beings with safety and efficiency. How we do that? Okay, so basically, this is the Robot Life Specification Problem. How we make this specification? Okay, well, and then this comes to us to this issue of cognitive things. Okay, well, nowadays it's very common to talk about cognitive systems and cognitive issues and cognitive robotics and cognitive things and cognitive Internet of Things, and we have everything cognitive nowadays. Okay, what exactly does it mean to be cognitive? If we go to psychology, we will see that cognition is the mental action or process of acquiring knowledge and understanding through thought, experience, and the senses. Or at least this is what the Oxford Dictionary tells us. So cognitions encompasses processes such as knowledge, attention, memory, working memory, judgment, evaluation, reasoning, computation, problem solving, decision making, comprehension, production of language. So, what exactly is something that we call cognitive? Well, we can understand something cognitive, or we can say that something is cognitive when this something employs some sort of technique in order to elaborate and abstract the information collected from sensors, in order to turn this information into knowledge, and using this knowledge in order to perform some sort of decision making, which will result in some source of intelligent behavior, intelligent action. Okay, so let's understand exactly how it works. We have sensing. We transform sensory information into knowledge, and then we perform some decision making into this knowledge and transform this into action, and particularly intelligent action. And this is to be cognitive. Okay, so let's keep going. Based on this notion of what is to be cognitive, we can then go to cognitive psychology and try to inspire ourselves in a field of cognitive psychology that is called cognitive modeling. And cognitive modeling is nothing else than building models trying to explain the cognitive abilities and psychological functions that we use when we are doing these things, when we are transforming and using knowledge for performing this intelligent decision making and intelligent actions. Okay, so the interesting thing on cognitive psychology is that even though some of these cognitive models could be only described in a psychological point of view, most of them are described in with this information processing point of view, and this can be very useful for us when we want to get this inspiration for constructing computational systems that are inspired on this repertoire or these capabilities, these cognitive capabilities. Okay, so these cognitive abilities or cognitive functions, they can be described using this repertoire of terms originated from psychology, and then we can try to describe computational models that are inspired in these cognitive models. Okay, so we can have computational implementations of perceptions, emotions, memory, decision making, behavior, motivations, learning, even consciousness. We have some specific computational models for consciousness, and we have a field of research nowadays that is called machine consciousness, language, metacognition, social cognitions, and other models like that. Okay, and then when an interesting concept that was introduced in 95 by Stan Franklin is the concept of artificial minds. What is an artificial mind? An artificial mind is nothing else than a control system for an intelligent agent. And this artificial mind is built upon these computational cognitive models that integrate multiple cognitive algorithms or cognitive services in order to create a full architecture to control these intelligent agents. And then what arises from here is exactly this notion of a cognitive architecture. And what is a cognitive architecture? A cognitive architecture is a general purpose computational architecture providing the basic infrastructure to the construction of artificial agents. So we can understand a cognitive architecture as an integrated model of a human mind, or at least a human-like mind. So what we are trying to do here is to implement computational versions of cognitive abilities like perception, emotions, memory, decision-making, reactive and deliberative behavior, motivations, learning, and in some cases, consciousness, language, and social cognition. And the interesting thing here is that what people is doing is using these cognitive architecture to control robots. And this is the interconnection between what we are talking about later, I mean, this idea of the robot life problem and the intersection of this problem with the idea of a cognitive architecture. Why? Because we can see that the robot life problem brings a lot of challenges to the construction of cognitive architectures. Okay, so how we can conciliate, for example, the different kinds of behavior that are possible for a robot. For example, we can see that we have at least 3 different kinds of behaviors that we can have for a robot. We can have a goal-based behavior, for example, when a robot is seeking, it's pursuing some sort of goal, some sort of future state that it wants to achieve. Or we can have a purely reactive behavior, for example, when we have the robot, for example, just reacting to some sensory input to the robot. Or we can have, for example, some kind of exploratory behavior with learning, when the robot wants to explore some new situations and see what is happening later. What we need is a cognitive architecture controlling all of this. A cognitive architecture that is able to command goal-based behavior, reactive behavior, exploratory behavior, and that is able to integrate all those behaviors in order to coordinate a very sophisticated behavior and make the robot to perform just like we expect them to perform. Okay, and then we have this problem of the robot life specification. How to specify these multiple motivations with its preference and priorities, with these different time scales, with these multiple realization horizons, how to properly occupy the use of time without losing time with unnecessary behavior. We don't want the robot to just spend time without being necessary. We want the robot behavior to be useful. Okay, we want the robot to maximize its utility for us. We want the robot to manage its self-maintenance with actual work. So how we do that? Okay, this is actually a very big challenge to cognitive architectures. Okay, and to show that, we are going to use an example that is a project that we are working in our research group in the University of Campinas. This is a project, the Troca project. The name Troca is basically based on this acronym, Transportation Robots with a Cognitive Architecture. It is a project funded by the Ericsson Research together with the University of Campinas. We are making, it's a simulation, it's not a real robotic project, because we are still in a stage of understanding things, and the cost of making this kind of experiments with real robots is still too much, too big. And so we are still working with simulations, but we are now planning to move to real robots. So we are in the stage of making the movement to the real robots. But this project here we have developed just with the simulator. Okay, so we have simulated this factory or warehouse environment using the Copilha robotic simulator and the ROS, the robot operating system. And basically what we are doing in this project is developing a robot that is able to perform a lot of different tasks. And basically this robot is a robot that can be operational for 24 hours. Okay, so it's a robot that can be responsible for its energy maintenance and other things that we will expect for a robot to maintain by itself. Okay, so the main tasks for the robot are the package transportation. We expect the robot to transport packages from inside the warehouse. Okay. Besides that, we expect the robot to perform some kind of environment exploration. So the robot don't need to know a priori the full warehouse. It should perform a warehouse inventory. So it should be passing through the warehouse and looking for the different boxes and checking if the boxes are in the the places where they are expected to be. Okay, if they are not, they are expected to report that to the system. Okay, it should be able to perform the energy management, so it should be checking its own energy level, and if this energy level is below a certain threshold, it needs to go to an energy station and recharge. Okay, it does that by itself. It needs to deal with human operators, so they are crossing the same ways that people could be crossing, and so they need to be aware that people could be crossing in front of them, and if this happens, they need to stop and wait until people cross. Okay, they also need to deal with other robots, so if there are other robots in the middle of the way, they need to negotiate such that they decide which one is going to have preference, and then they decide which one is going to go first. Okay, and they also do self-monitoring and benchmarking. Okay, so these are the duties that we are expecting for the robots to perform in their life, in their daily life. Okay. Well, this is basically the robot. This is, even though it's a simulated robot, we have designed the robot to be at least buildable in the future. So it is based on real robotic parts. So the mobile part is based on the Mir 100, which is an industrial mobile robot base that could be bought and used for mounting the robot. And also UR5 arm that can be used to pick the boxes and store the boxes in this internal shelf that you can see here in the picture. Okay, these boxes, they have this augmented reality code, and the interesting thing of this augmented reality code or AR code is that we have very good libraries for treating these AR codes with OpenCV, and we can use a simple camera, and then these libraries in OpenCV can give us a 3D pose for these AR code, and with that we can have a very good positioning for these boxes in the real world. So even though it's a simulation, we can have these in a very realistic scenario that we are going to be constructing later in the future. Okay, we have a gripper in the point of the arm that can be used to pick these boxes and to place these boxes in these slots inside the shelf and transport these boxes to its final destination, trying to attend transportation requests. Okay, so basically this is the dynamics of the robot. Okay, so this is a typical scenario. Okay, we have a shelf full of boxes like this. The robot can have some view for knowing where it is putting each of these boxes in its internal shelf. Okay, this is a view of the full factory. We have these processing cells, we have these warehouses on the back. This is a different view of the same scenario, also a different view of the same scenario, also a different view. And this is the general architecture of the simulation. We have different transportation robots that can communicate with the general manager. We have also human operators that in our case are simulated by a simulator that will simulate these human operators. posting transportation requests and asking for the robots to make the transportation from one position to another position. And these transportation requests stay on the general manager, and then the transportation robots can receive this information from the general manager and decide how to attend these transportation requests. Okay. Well, we have a cognitive architecture that is constructed using our technology that we are developing in the University of Campinas. We are using the CST. CST is a Cognitive System Toolkit. Unfortunately, I don't have too much time to talk about the Cognitive System Toolkit. If you are interested, we have a website with a full tutorial for the Cognitive System Toolkit. You can try to contact me later and I can give you more information about that. It's an open source toolkit that you can use for your own projects if you wish. Okay. Together with the CST, we have this CST reference cognitive architecture, and we are using a specific theory that we are which is called the dual process theory, that we are using for constructing a specific cognitive architecture that we are using for in some sense solving or at least trying to handle the Robot Life problem. And we will be using our cognitive architecture as a demonstration on a possible way to solve this Robot Life problem. Okay. Well, the dual process theory is a theory that our mind can be split into two different subsystems, which are called System 1 and System 2. This theory have become very popular by the economist Kahneman, that has made it very popular in his book Thinking Fast and Slow. And basically, the System 1 is the old mind. It is the subconscious mind, the parallel mind, which is fast, high capacity, non-conscious, and automatic. And we have also the System 2, which is the new mind, which is slow, limited capacity, which is serial and conscious, and usually responsible for sequential planning and things like that. And our cognitive architecture tries to use these ideas, and so we have developed this MECA cognitive architecture, which is also have been developed under development in this project together with Ericsson since 2015, and uses a CST as a background. It is a hybrid cognitive architecture that mixture subsumption architecture, it's a more numeric kind of cognitive architecture, together with a more symbolic kind of cognitive architecture that is based on traveler salesman problem kind of planning system. Okay, so it is an instance of this dual process theory, where System 1 is implemented by a dynamic subsumption architecture enhanced by emotion and motivational subsystem, and System 2 is based on TSP for planning, enhanced by a motivational subsystem, a consciousness mechanism, a scene-based episodic memory subsystem, and an expectation-based mechanism. Okay. Well, this is basically a draft of the Troca cognitive architecture. Unfortunately, I don't have too much time for entering into the details, but I will give a brief of the inner working of the Troca cognitive architectures for you to have at least an idea on how it works. So System 1, as I said, is based on a kind of a subsumption architecture. And in this subsumption architecture, we have basically a set of sensory codelets, okay? A codelet is basically a kind of a process that is called periodically from time to time, a time-based kind of process. In our case, we have a camera codelet that receives information from a video camera. In this particular case, this camera codelet is, we receive already this camera image already processed by OpenCV. So we already received the poses of all the AR tags that can be detected by the camera. So we are not receiving here a full RGB camera image, but we are receiving in this codelet this image already processed by the OpenCV. And so we are receiving the poses of all the AR tags that can be detected on this image. Okay. The laser rangefinder, we are receiving the information coming from we have two laser rangefinders on the front and the back of the MIR 100. We have a socket codelet where we can have socket communication with the general manager. We have a battery codelet that receives information from the battery level from the robot. We have a SLAM codelet where we can receive information from a SLAM ROS node that is installed in ROS. And we have also a feedback codelet where we can receive information from a ROS node that is controlling the pick and place system for picking and place the controllers of the UR5 robotic arm. Okay. On the motor subsystem, we have a controller for the MIR 100 where we can send commands for the MIR 100, basically to move the MIR 100 platform around the floor. Okay. The same happens for the UR5. We have commands that we can send for the UR5 through ROS, so we can command the UR5 to pick and place. Then we have a ROS node that performs a fixed set of commands that commands the robotic arm for picking and for placing the boxes. We have the socket that is performing socket communication with the general manager, and the display motor coder that is just sending messages to the display. Okay. In our behavioral and activity subsystem, we have three different codelets that are quite interesting. Unfortunately, I am seeing here that I don't have too much time for giving you the details. But the interesting things here is that we have two different kinds of actions that we can talk about. The simplest one is what we call an activity. So, for example, we can have activities like moving. Okay, so one possible activity is for the MIR 100 to move to one position to other position. So we have a single controller that controls the movement. We can have another controller that is doing only the pick and the place of the UR5 robotic arm. We can have activities for sending messages for the general manager, for receiving messages and things like that. And then the behavioral codelet is a codelet that performs the concatenation of sequences of activities. Okay, and then we have these activity tracking codelets that is responsible for monitoring the sequencing of these activities in a sequence of activities that forms a plan. For example, in order to attend a transportation request, I need the robot to first move to a position, and then after it reaches this position, it picks a box and places this box inside in an internal slot. Then it needs to move to another position, and then it needs to pick the box and place it into an external position. Then the transportation request was attended, and then it can move to another position. Okay, so the behavioral codelet works just like a concatenation of many different activities that are coordinated and controlled by the activity tracking codelet. Okay, well, we have many different motivational codelets. Okay, these motivational codelets, they are responsible for defining needs that the robot needs to satisfy. Okay, so I have here this energy motivational codelet, the danger avoidance motivational codelet, the transportation motivational codelets, the curiosity motivational codelet, the consistency motivational codelets, the human care, and such and such and such. Okay, we also have 4 different behavioral codelets and 5 activity codelets, and they bind together in order to form this behavioral and activity subsystem. It's important to say that this is a working architecture, so it's not just a conceptual one, but this is something that we have implemented in software, and we have run experiments with that. Okay. In system 2, we have the planning system. So the interesting thing here is that that planning system, they are asking the system 2 for plans. So I ask a plan, the system 2 then deliberates and then sends a plan for system 1, and then system 1 executes this plan. Okay, this maybe it's not so easy to understand, but this is how the full architecture works together. Okay, well, how we handle the robot life specification problem with this architecture? The first step is to assign the responsibilities in terms of motivations, and this is the tricky part of it. So how we do that? We need to think about in terms of needs. The robots should engage into activities satisfying the needs they are programmed to have. And these needs are related to the responsibilities and duties we expect the robot to perform during its daily life. Okay? And what are those needs? We need to talk about maintenance and life preservation needs, service needs, and enhancement and evolution and learning needs. So these are the 3 basic kinds of needs that every robot needs to have in its life. Okay, the robot should be able to evaluate how close or far it is from satisfying a given need, and these needs can be short-term or long-term need. For example, there might be a need, for example, that is to survive, so I cannot collide. And there might be a need that could be, or I cannot allow, for example, to be without energy. Okay, so this is something that we need to avoid. Okay, some needs might have a higher priority among other needs, and we can think about a whole hierarchy of needs. Okay, And we also need drives, and drives are the measure of the level of dissatisfaction of the needs. The higher the drive, the higher a need is dissatisfied and requires some action to be taken in order to reduce this dissatisfaction. Okay. Well, then we need to assign responsibility in terms of this motivation. So let's go to the example. In our case, the maintenance and life preservation needs are the energy management and motivation, that in our case it's an energy drive, and a danger avoidance motivation, in our case a danger drive. The service needs are a transportation motivation, a transportation drive, a consistency motivation, a consistency drive, a human care motivation and a human care drive, communication motivation, a self-criticism motivation, and our enhancement evolution and curiosity motivation. So I'm showing you, in our case, what are the needs that we have used to solving our robot life specification problem. Okay. Then the next step is to specify the robot motor capabilities. In our case, for example, we need to think about the navigation capabilities, the kinds of object capabilities, the possibility of handling objects, for example, the communication capabilities. Then we need to design this behavior and activity subsystem, the possible motivated activities, the possible reactive activities, the possible exploratory activities, and the possible coordinated activities among them, forming sequential behaviors, just as I said. We need to define the time scales, the priorities among activities, the situations where reactive activities take over the control, replanning requirements, etc., etc., etc. Okay. In our case, we defined that the system needs to move around, to pick and place packages, to recharge batteries, to exchange information with the general manager, to display the information. The activities that we have designed are to move to a location, to pick a box, to place a box, to send messages, to exhibit messages. And the sequences are: go to an energy spot, go to avoid collision, provide a transportation, or make an exploration. We can have some priorities. For example, avoid collision is prioritary among other possibilities. Older transportation requests are prioritary over new ones. Go to energy spot is prioritary if battery level is below 20%. Okay. Then we need to think about the necessary knowledge that we need to cope with. So we need to think about maps, objects, properties, parameters, the kinds of sensors, networks inputs. If we need some kind of SLAM, path planning, path following, vision systems, learning, reasoning, all of those things that we need to have a cognitive architecture to provide to us. Okay. In our case, for example, we have defined all those things here in order to make it to work. Okay. Well, what exactly is the challenge that we have here? Okay. Well, are current cognitive architecture robust enough for addressing all the aspects of the robot life specification problem? How to integrate multiple cognitive technologies in order to build a complete and integrated life specification for a full-time operational service robot? How similar this robot life will be or can be to an animal or a human life? Do we want this similarity? Can we benefit in any way from it? So you can see that this talk is just a start. It's a kind of provocation. You can see that we are here just raising some questions for you to think about. And the point is, how can we address this issue in a more formal and organized way? How this topic can be discussed in a more proper way by the community. This is basically what we wanted to address with this talk. Okay, so for the near future, we can see that more and more this idea of a robot life problem will become a relevant problem and will deserve a more deep coverage and a formal delimitation. More and more service robots will not be anymore just gadgets that we turn on and off, but will be 24-hour around us, and we need to cope with that. Okay, so we need to think about that, and a proper formalization of the robot life problem will be necessary and might help co-evolve in the field of cognitive architectures. And more, cognitive architectures that are capable of addressing the robot life problem might be more robust and would allow the overall development in the field of cognitive robotics and artificial intelligence, bringing significant improvements to our society. Okay, so basically this is the end of my talk, and I am now open to questions. Thank you very much.